All right. So here's 2005. Number 1. We got this fun looking graph here. Okay, so electric field diagram above, X versus Y. So we got positions, but we're just given the electric field lines. A, B, and C are all located at Y equals 0.6 meters. I guess the X-axis doesn't matter a whole lot. Which of these 3 points is the magnitude of the electric field the greatest? So the electric field is going to be the greatest where the electric field lines are closest. Density of electric field lines tells us how strong or weak an electric field is. So where the electric field lines the densest at point, what am I writing in red? At point C. Because that is where the electric field lines are densest. Or the closest together, whatever you want to say. All right, cool. Where has the, or which of these points is the electric potential the greatest? So electric potential, electric field, I guess I should say, points from high potential to low potential. So if we look here, right, our electric fields almost all are pointing to the right or the right-ish. So which of these points is going to have the highest potential? It's the one that's going to be the furthest to the left because potential or electric field lines point from high potential to low potential. So which of these 3 points is the electric potential the greatest? It's got to be point A. Point has an N in it. A is capitalized. Really doing quality stuff here. Point A, because the field points from high potential right, the field's pointing right, which means furthest left. Is the highest potential. All right, qualitatively, meaning without numbers, describe the, an electron is released from rest at point B. So we put an electron at point B, we let it go. Describe the electron's motion in terms of direction, speed, and acceleration. So the direction, which way is the particle going to move? So the particle, right, if we look here, electric fields go the opposite, or sorry, electrons go the opposite way of electric fields. So the electron will travel left. I can't spell travel. Against the electric field lines. Or towards high potential, however you want to say that. We've already established that to the left is the higher potential, so electrons will flow towards high potential. Electron will travel to the left against, I spelled against wrong too, Jesus Christ. Against electric field lines. The speed, the electrons' speed will increase as long as it feels a force from the electric field. I can't write anything right now. It's the end of the day. I'm tired. It's time to go home. From the electric field. So it's going to increase its speed as long as it's feeling a force from the electric field. Acceleration. The electron's acceleration will decrease because the field's weaker, right? As we move to the left, the electric field gets weaker. We can see those lines are spreading apart. They're getting further apart. It means we have weaker field, which means the electric force won't be as strong, so the acceleration won't be as big. So the acceleration will decrease because strength of the electric field is decreasing. And therefore the electric force is decreasing as well. So motion to the left, it'll speed up as long as it's in that field because it's going to feel an electric force. But the acceleration is going to get smaller because the strength of the electric field is decreasing, right? And acceleration is force over mass. So if the field is just decreasing and the force is decreasing, then the acceleration is also decreasing because the mass of the electron is probably not changing. Calculate the electron's speed after it is moved through a potential difference of 10 volts. So here we have to use a little conservation of energy, right? Potential energy is VQ. We know the potential difference is 10 volts, so we have something to plug in for V. That is the potential energy, right? This is electric potential energy. That is going to be converted into kinetic energy as our particle moves through that potential difference. So we're basically going to U equals K, right? Potential energy equals kinetic energy. So VQ equals 1/2 mv squared. This is capital V for potential. This is lowercase v for velocity. Velocity is what we're trying to solve for. So potential difference of 10. Q, charge of an electron, 1.6 times 10 to the negative 19th equals 1/2 mass of an electron, 9.11 times 10 to the negative 31st. I probably should be, I'm pretty confident. I know all about electrons. I don't need to double check that. And then we're just solving here. So let's take, this will just move this to the negative 18th. So 1.6 times 10 to the negative 18th equals 0.5 times 9.11 times 10 to the negative 31st. 1.6 times 10 to the negative 18th divided by that answer will give us that, and then we take the square root there. Sorry, I'm just doing this all on a calculator, but I got 4.56 times 10 to the negative 31st here, b squared. I divided that over, I got 3.5 times 10 to the 12th equals v squared. Take the square root, and we get a velocity of 1.9 times 10 to the 1, 2, 3, 4, 5, 6th power meters per second. 1.9 times 10 to the 6th meters per second as our velocity there. Oops. Okay. Points B and C are separated by a potential difference of 20 volts. Make or estimate the magnitude of the electric field midway between them and state any assumptions that you make. So what do we want to do here? Electric field equals V over Q. Maybe. Or no, V over R. Electric field. Let's do the whole. V over R. I think. I don't remember. Stop that. Let me double check. It is V over R. Okay. I was panicking for a second, but it is V over R. We could get that using the potential equation as well, if we wanted to, right? Potential difference equals the negative integral of E dot dr. If we say E is constant, which we should state as one of our assumptions. Right, and we take our, let me just work this all the way, delta V equals the integral of E dot dr, right? If we say, okay, E is constant, that pops out. We just get the integral of dr. Integral of dr is just R. It's a straight line between B and C, right? So we don't have anything weird with our dr, our line integral there. So we just get potential difference is equal to E times R. We resolve for that and we get E is equal to potential difference divided by R. So we have E equals potential difference of 20 volts divided by R, which is the distance between B and C, which if we look here, looks like we go from 0.09 to 0.08, so 0.01 will give us 2,000 newtons per coulomb as the electric field strength. On the diagram, draw an equipotential line that passes through D and intersects at least 3 electric field lines. So we want a line that goes through D and also passes 3 other points. So potential difference, right? We want the line to be perpendicular to our other lines here, but we also need it to go through D. So how do we make a line that goes through D and is also perpendicular to at least 3 other lines? I think it'll be something like that, right? Perpendicular, 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 perpendicular. And we get something that looks like that, right? Through point D, perpendicular to all the lines or all of the, electric fields as we go along there. So that's kind of what we should have in terms of the equipotential surface. Cool. All right, so there is number 1. Let's stop this recording. Of course.